Morning, everyone. So I want to review with you some of the main ideas that we learned from the relativity section. This is where the physics got to be really, really strange, especially when objects start traveling close to the speed of light. The physics that we've been learning up to this point has been referred to as Newtonian physics. So all of Newton's laws, F net equals ma, all the kinematic formulas with acceleration and all those ones there, they work for everyday speeds. We had actually calculated we would need to travel pretty close to the speed of light before you actually start seeing some sizable difference. But we're going to, especially as we look at light does travel at light speed, so definitely that's going to come into play. Throughout this chapter, we started looking at little like spaceship models. If spaceships can get close to the speed of light, we found that things that we traditionally thought to be constant actually end up changing, end up becoming relative, which is very strange. We find that time relatively it slows down. We find that length typically gets shorter and the mass increases. Because the mass overall increases, it gets a little bit harder. You need even more force to accelerate it even faster. We're going to see in this section again, the speed of light actually represents some maximum speed that we can travel in a universe. That's the limit. Not only does our physics get really, really strange, you can't actually get faster than the speed of light. So let's just rehash some of these key ideas here. First thing is we are talking, this is Einstein's law of special relativity. So the type of relativity that we're talking about here is of the type, when it says special relativity, we are working in what's referred to as an inertial reference frame. Inertial has this notion of inertia. Inertia is basically a sort of resistance to motion. It's similar to momentum, but for us, inertial, for special relativity, we're going to say inertial means there is no acceleration. Einstein came back about 10-20 years later on and he developed the law of general relativity. So he found that the universe was actually expanding. He actually applied some of these concepts to the accelerating frame of reference. So for Einstein's special relativity here, instead of keeping our traditional, time is constant, everyone agree that these are simultaneous events here, he actually just ended up with two principles. The first principle had this notion here, there is no preferred reference frame. So in this case here, there is no preferred, I can call it a reference frame here, or you can say it's no preferred point of view, if you like it that way. So we did this analogy here. Let's say you're person A, right, and you're standing on the earth. Person B is standing in front of you, and he's on a train, and he's having to travel to the right, relative to you, right? So according to you, right, according to the Earth observer, because you're on the Earth, A, okay. B is moving to the right, and let's give it a speed here of 10 meters per second, right? So there you go, perfect. I am in an inertial reference frame because I am not moving, and then this one here is constantly sliding to the right. However, if I ask person B the same question, person B, if you're standing on this train, it's like you're just staying stationary. Right? I'm not actually physically moving, but it's like as the train moves by, the whole world moves by you in the opposite direction. So relative to person B, you are on this train, you're going to actually see, person A at first was sitting in front of you, but the whole world actually moves past you in the opposite direction. So in this case here, according to, we'll call him the moving observer, according to the moving observer B, it's actually A that's moving. A is moving to the left at, we could actually say negative 10 meters per second. Right? Velocity here is direction, so negative 10 just implies it's actually leftward. Right? And the question here is who's right? Okay. Well, in fact, both of them are right. We talked about during our lessons here, we sort of lean towards, B is actually like, he's not in the know, right? B actually doesn't realize he's actually on the train. He's actually the one moving. A is actually stationary. Well, what if, we're on the Earth's surface, right? What if someone else was actually in space and actually saw the revolution and the rotation of the Earth's surface? So even A, which we sort of lean towards and its preference towards it, A actually will rotate every day. It rotates around once, right? 24 hours. A is actually moving as well, and A has no idea, regardless of who you talk to. The Earth observer, the moving observer, some other observer elsewhere, nobody has a better view than anyone else. Just according to who you are, according to what you are doing in your inertial reference frame here, the numbers may actually differ. Right? So That's a little bit strange here. All our Newtonian physics, all our laws here will work regardless if we believe A, we believe B, even though the numbers themselves may be different. The big thing for Einstein here was the second principle here. This was the notion of constancy of light. The one thing that he kept constant was not, oh, mass has to stay fixed or length has to stay fixed. Constancy here had this notion, the speed of light is actually constant, we actually know the number, in any reference frame. So time can actually slow down, lengths can actually get shorter, mass can actually increase. The thing that I want to keep constant is everyone would agree that the speed of light is 3 times 10 to the 8. Right? Now this is a little bit strange. Okay, we'll deal with that relativistic addition formula first. So relativistic, so when we start getting up to relativity speed, so close to the speed of light, relativistic addition of velocities. Let's do the Earth case first. Well, the Earth case is, well, I just did person A, person B. Let's say person A is just standing there. So person A is at rest. He's at 0 meter per second. Okay, I'm going to have person B. Person B is going to walk by him at 10 meter per second like we said. And little do I know, person B is actually holding onto an object, and he ends up throwing the object 5 meter per second relative to him. Right? So according to person B, right? So according to B, okay, this object, the ball is thrown at 5, right? Because person B sort of ignores that he's actually moving. He's just hanging on to the ball here. He throws the object at 5. He says 5. Again, our Earth observer, person A here, who is currently not in motion, person A will not only see, yep, the ball was thrown at 5 relative to that person, but B, don't you realize you're also moving? A would actually think the ball is actually moving a little bit faster. So according to A, the ball is moving the 10 meter per second that the guy is moving plus the 5, A is actually moving 50 meter per second. So it's now faster than the 5 that you said. Turns out when we get close to the speed of light, our formulas are not so simple. It's not just going to be the total velocity is just u plus v. It's not just one speed plus the other speed. It actually gets divided out by 1 plus uv over c squared. Right? So what's going to end up happening here is, in this example, let's say a light particle zips by. So a light particle, a photon zips by, like we said, is 3 times 10 to the 8. Person A who is not moving, fine. I'm not moving, the light particle travels at 3.8. But the guy is actually moving 10 meter per second, sort of along with the light. Shouldn't person B say the speed of light is 3 times 10 to the 8 minus 10? What's really weird is, even though there is relative motion relative to him versus the speed of light, both of us would agree the speed of light is always traveling at 3 times 10 to the 8. Time may need to change, time may need to warp for you to make that true, but all of us, regardless whether I'm actually stationary, regardless of actually moving, notice it's still an inertial reference frame because I'm moving at a constant velocity. All of us would agree when this light photon actually passed by, it's actually 3 times 10 to the 8. Right? So let's do, again, we only see this example when we start getting upwards close to the speed of light. Let's start off here. Let's do this example. Person B is actually traveling at 0.7 the speed of light. Right? C is 3 times 10 to the 8. You can always plug that in. Person B, again, is holding this object here. Person B ends up throwing the object here at 0.4 the speed of light. If this were not relativity, we'd say, okay, person A would see, well, it's the guy's speed, and it's the speed that he throws it at, 0.7 speed of light times plus 0.4 the speed of light here. It's actually 110% the speed of light. We're actually beyond the speed of light. Well, because we are getting close to speed of light, we actually want to use this formula here, the relativistic additions, and we'll see what we get. So according to person A, according to the Earth observer, A, I'm going to imagine that he's just standing there. The total speed, how did these velocities end up adding? Sure enough, it is going to be 0.7 c plus 0.4 c. Those speeds there add. At first, that's the worrisome piece, because that would amount to 1.1 c. Oh no, I'm breached the speed of light. I'm actually faster than the speed of light. Well, mathematically in our formula here, 1 plus, as you do the bottom here, 0.7 c times 0.4 c all over c squared. The c's end up canceling out. That's why usually if you express velocity in terms of c, it's a little bit nicer. Well, the bottom here, phew, this saves the day here. 0.7 times 0.4 is 0.28. And then if I add 1 to that there, that's going to be 1.28 here. At least this fraction here is going to be less than 1. Phew, we're actually still slower than the speed of light. The speed of light is a maximum speed. You can't get beyond that speed here. And that ratio here, what is 1.1 divided by 1.28? Well, I'm actually, in this case here, 0.86 the speed of light. At any given point, you can actually calculate what that speed is. Because we've rounded the speed of light here as 3 times 10 to the 8, you can just say, well, what is 0.86 times 3 times 10 to the 8? It's still going to be ridiculously fast. Take the whole number times 3e8. So it gives me, give or take, 2.6 times 10 to the 8. It's still ridiculously fast, but that's going to be thought of as 86% the speed of light. So now we're going to switch over to the other main formulas here. We did the whole derivation for you. I'm not going to repeat it for you here. Basically, these are the consequences. As we get close to the speed of light, we have what's referred to as time dilation. Dilation means it slows down. In our formula sheet here, on the corrected one, we say T naught is equal to T root 1 minus v squared over c squared. Mass actually increases. Mass gets larger. In that case there, it was m naught is equal to m over 1 minus v squared over c squared. And then we have our length actually contracts. The length that I'm talking about is just the parallel distance. And therefore, that's also getting smaller. So L naught equals L root 1 minus v squared over c squared. Here, you need to be careful of sort of which textbook that you're using. Sometimes they actually use T naught for the other variable. So just depending on how you define your variables, make sure you are saying that the moving time, so this one here, this is for the moving observer. Right? This is sometimes referred to as the space-time, right? Because it only comes into play when we start traveling at spaceship speeds here. This one here, to be, I don't know if it's simpler, but one way of framing it, you can say this is at rest with the phenomenon. So if I'm sitting on the spaceship and the spaceship has no windows, I would have no idea that I'm actually moving. That's the time that I'm talking about. That's the mass I'm talking about. What's confusing, however, is even though that's at rest with the phenomenon, this is still relative to the Earth observer, relative to the ground observer. Right? That's what the ground observer would say that this one is moving at. The other one here, this is the T, the M, and the L here. This one here is relative to the Earth observer. This is the person that's watching it happen. Right? The time typically travels a little bit faster, masses are a little bit smaller, the lengths are a little bit longer, but that's according to the Earth observer. So just trying to save yourself from, is this relative to Earth or is this relative to space or whatever, just keep these general conclusions in mind. Time has to have slowed down as you move faster. Mass has to have increased, length has to contract. They sometimes shorthand this one here. They call this lowercase gamma here a relativistic factor, and they actually do 1 over 1 minus v squared over c squared. And basically, again, sometimes they even define the relativistic factor as just this root factor, so the formulas get to be really, really funky, but just on our formula sheet here, everything is consistent. Let's just work through a problem so we make sure we're on the right track. So let's have a problem here where we have I'm just standing on the Earth, so I'm person A. Person B here is sitting on a spaceship. The spaceship here happens to be 100 kilograms. According to the Earth observer, this person, the spaceship here is 50 meters long. You'll notice that I'm never caring about the width of the spaceship. And let's say this time, this spaceship actually travels at 2.4 times 10 to the 8 meter per second. That is its velocity, right? A couple questions for you here. I want to know, as time has dilated, I want to know, calculate, just to keep simplistic here, I can say calculate the relativistic, the weird slowed down time, relativistic time, the relativistic mass, and the relativistic length. Right. Totally okay, you can just use 2.4 times 10 to the 8. I usually like reframing it in terms of C. If I go 2.4 E8 divided by 3E8, that gives you the ratio 80%. So this means this number can actually be written as 0.8 C, and that way it saves me the hassle of actually punching in C multiple times. I saw C in a lot of my formulas. If the C's end up canceling out, we just cross them out directly. So let's just try this out here. Hopefully not too bad. Our T naught is equal to T root 1 minus v squared over c squared. I haven't given you a time that it travels for. Let's say he travels for 2 hours. So if the time is 2 hours, pretty much I just want to calculate what this root 1 minus v squared over c squared term is going to end up being. At everyday speeds, v is a lot less than c. So that means this v squared is a really tiny number in comparison to a really big number. This fraction is close to 0. 1 minus 0 is 1. Root of 1 is basically 1. So therefore the times pretty much agree. But now that we are traveling close to the speed of light, let's calculate what this root term ends up being. 1 minus, you could totally type in 2.4 times 10 to the 8 squared. But since I have it already reframed in terms of c, I'm going to type 0.8 c all squared divided by c squared. I'm just going to clean up what's underneath the square root here. When you square a product like this, is 0.8 squared and c squared. That means the c squared is going to cancel the c squared. This would now be 1 minus 0.8 squared. 0.8 squared is 0.64. I can do the underneath the square bracket. 1 minus 0.64 is 0.36. And we've actually calculated that underneath the square root is 0.6. Right? So therefore, this factor here has become a decimal. So according to the space-time, which has slowed down, what is 2 hours times 0.6? It's like only 1.2 hours has passed by. Right? So let's see which clocks we're talking about. The clock on the Earth time says 2 hours has passed by. Right? I watched the spaceship travel for 2 hours. I have nothing better to do with my time. According to the person on the spaceship, because he's moving, time slows down for him. So according to his watch, it only seems like 1.2 hours has passed by. All right? So there's our time dilation here. I figured out what this root 1 minus v squared over c squared is in this problem. Looking at our formulas for the length. Length is basically the same formula with the 1 minus v squared over c squared without doing the same derivation. The length of it was supposed to be 50, and then we have 0.6 here. Length gets shorter, 50 times 0.6. He's going to now say that the spaceship is only 30 meters. So it's like the spaceship has actually gotten shorter as we actually start traveling faster. And similarly for the mass, although the formula is different here, m naught is equal to m over this fraction, 1 minus v squared over c squared. If the overall mass was 100 kilograms, I expect the mass to get heavier. We dealt with what this root ends up as. So 100 divided by 0.6, this gives us here 167 kilograms. And that's generally going to be true here as you get closer to the speed of light. As we get closer to the speed of light, the mass increases, making it harder to accelerate more. And that's why by the time we actually hit the speed of light theoretically, right, it's an impossibility because time would have stopped, okay, but if you can theoretically get to that there, you would need an infinite amount of force to allow for an acceleration. Well, you can't supply an infinite acceleration, and that's why it represents a maximum speed. Right? So the sort of conclusion out of there here is the speed of light, yes, I know I've rounded it, it's actually 2.99 times 10 to something like that, but the speed of light is the maximum speed in our universe. Because of these relativity features, because time is slowing down, the mass is increasing, things are getting shorter, we can't actually get beyond the speed of light. Right? We did a quick little analogy over to half-life. So a lot of the synthetic elements here, we sort of create an element. It only has a half-life of like microseconds, things like that. What we can do is we can send them around what are called particle accelerators here. Because those particles are fairly light, it's really easy to speed them up close to the speed of light. And because their time slows down, I can actually study that particle for a little bit longer. So let's just switch over to just rehash a little bit with a half-life. Make sure you know this definition here. For half-life, half-life is the time needed for half the sample to decay. Now we know based on conservation of mass here, maybe it's not like the matter has actually vanished, but at least the radioactivity, the sort of the dangerous intensity here has actually dropped by half. Right? So let's just do this by way of a question here. Let's say I start off with an 80-gram sample. An 80-gram sample decays to 15 grams in 30 minutes. I want you to A, calculate the half-life, and B, find the percent remaining, not the percent decayed, but how much is left if in part B, find the percent remaining after 60 minutes. Right? First thing I would do in these questions here, I'd start off with a picture. Sometimes they work out the numbers so nicely, we don't even need to worry about the exponential, that scary formula. We can just start with a picture. I'm starting off with 80. After one half-life, I expect it to be 40. I've lost half, right? But now that I have half the sample, I'm not going to lose another 40 in the next half-life. I'm only going to lose half of what I had. In this case here, I have 20. You can use t half as a symbol or k as a symbol. It doesn't really matter. Another half-life here, I now have half the number of particles. Now I'm down to 10 grams, right? So they said we went from 80 grams to 15 grams, and it took us a total time of 30 minutes. This time here, it was not exactly on a exact match of half-life. So all we're going to have to do is we're going to have to use the half-life formula. So also on your formula sheet here, nt is equal to n naught, 0.5 t over k. So you rehash some of these terms for you here. Nt is the final amount. This is the amount that's left over at time t. N naught stands for initial. Right, we use that naught symbol for initial before. The t is the actual time that's elapsed. It's the actual time that passes by, whereas the k we're using as our half-life. So how long until half the sample decays? So let's try it out here. Let's plug and play here. The amount that's remaining for us was 15. We had started from 80. Every time we have a half-life, it drops by 0.5. That's why that's my exponential decay there. I have waited an actual 30 minutes. So 30 minutes. That's been, based on my picture, has roughly been 1, 2, and a bit half-lives. I just don't know how long the half-life is. I'll just leave that as k. So let's just solve through the math here. 15 divided by 80. This gives me 0.1875 is equal to 0.530 over k. It's just mathematically a little bit harder. I do want to solve for k. Unfortunately, the k is in the power. So what we're going to do, exponent and log are inverse of each other. You're going to take the log of both sides. I don't care if you use on your calculator common log, like log, or natural log ln. Just use the same log on both sides. So in this case here, take logs of both sides. So it's going to be the log operator, 0.1875. When I take a log of this, it basically undoes the exponent for me. And basically it brings this power back down. It brings the k back so that I can work with it. Now what I have is I have log 0.1875 is equal to 30 over k log of 0.5. And now it's just a little bit of algebra here. This is now just a multiply. So I can divide the k up and I can divide the log 0.1875 down there. So k is equal to 30 times it by the log of 0.5. Log is an operator. It has to apply on some number. So in this case 0.5. And I'm going to divide it by log of 0.1875. So by doing this here, the math was a little harder. 30 log 0.5 divided by log of 0.1875. This one here gives me the k is 12 minutes. Does that make sense? Well, let's try it out. After 12 minutes of time, we have lost half. After another 12 minutes, so I've waited 24 minutes, right? I've lost another half. In this case here, coincidentally, it was actually just 6 minutes and I actually lost half. Normally, it doesn't work out like that because in this formula, we're actually expecting more of an exponential decay. At first, when you start off with lots of particles here in time, at first you're going to lose half, so 50% of what you had before. Then you're going to lose half of that, 25% here. You're going to actually lose things much quicker at the beginning and much slower afterwards. So even though coincidentally this time it ended up working out really nicely, I would still work through the math. So my half-life is actually 12 minutes. You'll find part B of the question here is actually a little bit easier. Part B says, now that I know the half-life, what if I wait 60 minutes? So 60 minutes here is twice the time, right? You can sort of work out, Well, 60 minutes actually, because 60 minutes is perfectly 5 half-lives, I can just work this out. I can go, well, we were at, so 80, this becomes 40, this becomes 20, this becomes 10, half of that becomes 5, half of that becomes 2.5, half of that becomes 1.25, right? So because I know a half-life is now 12 minutes, and because 60 minutes is exactly 5 half-lives, I did the right 1, 2, 3, 4, 5. Oh no, sorry, one too many there. Because 60 minutes is 5 half-lives, I already know the answer should be 2.5 grams. That's how much remains. So that's why if it sits on the order of a half-life, you can actually figure out that number without actually punching into your formulas. Just do a double check for yourself. Is that true? NT is equal to N naught. I'll leave this for you to verify. How much remains? So the NT is a question mark here. You started off with 80. You're going to 0.5. The actual time that we're waiting is actually 60 minutes of time. 60 minutes divided by 12 there. That's going to become to the power 5. So 80 times 0.5 to the power 5 should end up being 2.5. I'll let you verify that for yourself. Right? So keep practicing through your worksheet and let me know if you have any questions. Thanks, guys.